Welcome to Maths with EJD. In this video, we're looking at differentiation of vectors. And the first part here is about velocity and acceleration as derivatives of position vectors. Okay, we have that. So generally speaking, we need to pay attention to the idea of position vector, which can be represented as r of t or sometimes s of t. And this is simply a vector. It's simply a vector that represents the position of an object in space as a function of time, as a function of time t. So a position vector is a vector that represents the position of an object in space as a function of time t. So a good example is this. For an object moving along a curve in three-dimensional space. Of course, when we say three-dimensional space, we're talking about x, y, and z axis. In three-dimensional space, the position vector can be given by r of t, which is equal to x of t I. I, j, and k are the unit vectors, which we've seen before. Then y of t in the direction of j, and plus z of t in the direction of k. So where x of t, y of t, and z of t are the coordinates, are the coordinates as functions of time. Okay, so that is about position vector. Then, of course, we are looking at velocity and acceleration as derivatives of position vectors. So we have seen what a position vector looks like. It is simply a vector representing the position of an object in space as a function of time t. So now let's talk about velocity vector. Velocity vector. So velocity vector. So the first derivative of the position vector with respect to time, which okay, the velocity vector, right? The velocity vector is the first derivative of the position vector with respect to time. So you have position vector as r of t, which is, x of t I plus y of t j plus z of t k, right? So the velocity vector now, v of t, is simply the r of t dt, simply the derivative of the position vector. And that is simply the x of t dt in the direction of I plus dy of t dt in the direction of j plus dz of t dt in the direction of k. So that is what you have as a position vector. So if you have this example, we have this, that if r of t is equal to 3t squared I, if r of t is 3t squared I, so it's 3t squared I plus 2t j plus 4k, then then the velocity vector, and the velocity vector is v of t, which is the r of t dt, and that is equal to d dt of the whole of r of t, which is 3t squared I plus 4 plus 2t j, 2t j plus 4k plus 4k. And that is simply differentiating term by term. So you have d dt of 3t squared, then in the direction of I, then d dt of 2t in the direction of j, plus d dt of 4 in the direction of k, right? So, of course, we just apply simple principles of differentiation. Differentiate 3t squared with respect to t, you have 6t in the direction of I plus d dt with 2t with respect, differentiate 2t with respect to t, that's simply 2 in the direction of j. And of course, 4 is a constant. Differentiate 4 with respect to t, that's 0 in the direction of k. So that's just 6ti plus 2j. And that is what you have as position vector for that particular example. So we can move ahead to talk about the third idea, which is acceleration. You have acceleration vector, which is a of t. Of course, velocity vector is v of t. Velocity vector is v of t, right? So acceleration vector is a of t, so that we have the derivative of the, it is the derivative of the velocity vector with respect to time, with respect to time, or you can say the second derivative, of the position vector. So by the very definition of acceleration, right? When you differentiate velocity once, you get acceleration, or when you differentiate position vector twice, you get the acceleration. So it's all the same in that sense. So it means you're saying that a of t is equal to dv of t dt, which is simply the same thing as second derivative of the position vector with respect to t. One mistake I've been making is I should have put arrow on top of it, because a, v, and r, they are vectors. So it's important to never forget to put arrow on top of them. Really important. So if you're typing, you can make it bold. If you're not typing, it's easier to just put R. Okay, think that helps. Okay, do I need to this last three now? Yeah, I think just R is fine. Then R of t here, all of that. So here, R of t, really important. And this vector also important. Yeah, so don't forget. So that's what acceleration is. And then, of course, if you want to calculate the acceleration of what we've been looking at, that original position vector we considered, right? You had r of t, that example we saw before. We had r of t as position vector, which is actually 3t squared I plus 2t j plus 4k. That was our r of t. And from this, right, we got v of t. V of t is actually dr of t dt, and that is differentiating each component respectively with respect to t. So 3t squared gives you 6t, 2t, I mean, that's 2t in the direction of I, 2t is just 2 in the direction of j, 4k is 0, so, and that is all gone. So if you're looking for the acceleration at a of t, right? So that means you have dv of t dt, which is actually the second derivative. That's the squared r of t dt. And that means you differentiate. So that's d dt of 6t in the direction of I plus d dt of 2 in the direction of j. So that the acceleration a of t is now differentiate 6t, you get 6 in the direction of I. Then differentiate 2 with respect to t, that's 0 in the direction of j. Okay, so finally, the acceleration is simply 6I. Okay, and of course, the whole idea of magnitude and direction can still apply here by you taking the modulus. Okay, so that's the first part we are looking at, which is velocity of and acceleration as derivatives of position vectors. Now let's look at another concept when we talk about differentiation of vectors or vector differentiation, as you however you want to call it. So let's go back and talk about this tangential, tangential, and normal components, and normal components of acceleration. Tangential and normal components of acceleration. So, of course, if you have a curve, right, you say a line is tangent to the curve because that line that is tangent to it just touches it at a single point. And then you now have a normal to that line. The normal to that line is the line that makes angle 90 degrees with it. That's the geometry of the idea of tangent and normal. So now we want to see the sense, we want to see it in the sense of vectors. So the acceleration vector can be decomposed, can be decomposed into two components, because the first component is a tangential component, tangential component. So, and what does that talk about? It represents, this actually represents the rate of change of the speed along the path. So as you can see, tangent is like let the curve, and if you have a curve now, it's more like the path. So the tangent to it talks about the rate of speed, the rate of change of speed along the path. And that is simply a of t, at, which is the absolute value of v of t. This is a vector actually with respect to t. That's what is given, that's what is known as the tangential component. And then you have the normal component. We're talking about tangential and normal components of acceleration. So still talking about acceleration, but acceleration has tangential and normal components. So the second part is the normal component. Normal component. So here, the normal component represents the rate of change of direction, the rate of change of direction of the velocity, or the centripetal acceleration, or the centripetal acceleration. Okay, so the normal component represents the rate of change of direction of the velocity, while tangential represents the rate of change of the speed. Speed is a speed is actually a scalar quantity, and that is how we have the absolute value of the velocity here. So when you find the absolute value, you're actually getting you're getting a scalar quantity. So that is why that's for that. Then for normal component, now it is a rate of change of the direction of the speed of the velocity, which is a vector quantity in this case. And that is given as an, which is equal to the absolute value of the velocity vector v cross the acceleration vector a of t, all of that divided by the absolute value of the velocity vector v. So that is the normal component of acceleration. Okay. Now to drive this point home, let's take an example. We have this example. If an object moves along a circular path, along a circular path of radius r with constant speed v, the tangential component of acceleration is 0. You know, it's constant speed. So the tangential component of acceleration is 0. That means a sub t is equal to 0. Okay. While the normal component is given by, so if an object moves along the circular path, so like a circle like that, of radius r, which with constant speed v, tangential component of the acceleration is 0, while the normal component is given by an, which is equal to v squared over r. You know, we're talking about centripetal force. So that's v squared over r. So I'm sure that's like the velocity, the square of the velocity divided by the radius of the circle, of the circular path, like that. So that goes. And then let's look at the final part of this video, where we talk about higher order derivatives of vectors. Higher order derivatives of vectors. So higher order derivatives of vectors. Here, higher order derivatives of vectors are used to describe more complex motion. I'm sure some of these ideas may be new to so many people. So higher order derivatives of vectors are used to describe more complex motion. And of course, the first one there is actually the jerk, and that is the third derivative. Okay, the third derivative. Now that means you have position vector, differentiate it to get velocity, differentiate position vector, velocity, you get acceleration. Interestingly, you can differentiate acceleration to get what is called the jerk, J-E-R-K. That's the third derivative of the position vector. So we say the derivative of acceleration with respect to time is called the jerk with respect to time. So it represents the rate of change of acceleration, the rate of change of acceleration. What that simply means is that you can have j of t, which is a vector, to be equal to dA of t. Of course, A of t is acceleration. So dA dt. So that's like d squared v I mean, I can keep saying that. This is like d squared v. Differentiating vector the second time. D squared v dt squared. Okay? And that's the same thing as d cube r of t dt squared. Dt cube rather. That's like differentiating the position vector 3 times. That is the jerk. Okay? So that is what is called a jerk. And interestingly, we have the fourth derivative, which is called the snap. It is called the snap. Now, before we go too far, I think I have a kind of clarity on jerk. Let me see that. Let me see that. Okay. Yeah, let me add this for jerk. I think it's important to add it. So jerk measures jerk measures the jolt, what is called the jolt. The jolt, it measures the jolt experienced. The jolt experienced, we said it's complex motion, right? It measures the jolt experienced by an object. The jolt experienced by an object due to sudden changes, due to sudden changes in acceleration. So when acceleration suddenly changes, then what you have is a jolt, which is called a jerk, So due to sudden changes in acceleration, okay? So that goes. And of course, we have the fourth derivative, which is called a snap. You have what is called a snap. The snap is actually the fourth derivative. So you have this, and you can say that the derivative of jerk with the derivative of jerk with respect to time is the snap. So that describes changes in jerk, and the physical interpretation of this is that snap provides provides insight into the curvature of an object's motion trajectory. So it tells us a bit more about the trajectory of the motion of an object. That's what a snap is. So, I mean, the most popular part we've always known are the position vector. That's like the displacement, and then you know about the vector, and then you know about acceleration. But today, add it to your database that you can have jerk and snap, which describe complex motion. Now, before ending this video, let's take this kind of general example. So we have this, that for a simple harmonic motion, a harmonic motion talks about something periodic, something like what happens with a pendulum. So for a simple harmonic motion described described by, say, this r of t equals a, which is the amplitude, a cos omega t, then you have the angle and all that, a cos omega t I, plus a sine omega t j. Okay, so this is the position vector now. So we want to get all the things we've described so far. So first of all, we have First of all, let's start with the velocity. So velocity v of t is 0 of t. Velocity v of t is such that differentiate cos, you get sine, right? You know that we get minus sine. And then, of course, you have to differentiate the omega t inside first. So in that case, you have minus, this is going to be minus sine. So you have minus a, then the omega, when you differentiate omega t with respect to t, you get omega. So you get minus a omega, then sine omega t in the direction of I. Then differentiate sine, you get cos, that's still positive. So you have a omega cos omega t in the direction of j. So that is velocity. Okay. Now let's talk about the next thing we can have, which is the acceleration. Acceleration. So the acceleration, right, is the differentiating velocity with respect to time. So again, differentiate omega t, the omega comes out, and differentiate sine, you get cos. So that's minus a, then omega is squared now, omega squared cos omega t in the direction of I. Then differentiate cos here, you get minus sine. So that's minus a. Differentiate omega t, you get omega. So that's omega squared sine omega t in the direction of j again. So we have that. Then, of course, you can talk about the jerk. You can talk about the jerk. This now, you have the jerk, which is j of t, and that is equal to, now differentiate cos again. Differentiate cos, you get minus sine. So it changes sign now. So minus and minus, that's plus. So you have a, differentiate omega t, you get omega again. So you have a omega cube sine omega t in the direction of I. Then differentiate sine, you get cos, which is positive. So so this remains minus here, because minus and plus is minus. Then a, differentiate omega t, you get omega times omega here. So you have a omega cube cos omega t in the direction of j. Okay. Then of course we can talk about the snap. And talk about the snap. Of course, I didn't give the formula for snap before. We can say that snap is s of t. You can say it is s of t. Snap is, we can say that is s of t, which is dj of t dt. That's the rate of change of jerk. And that is the second derivative. That's the squared acceleration, the t squared. That is the cube velocity, the t cube. And that is the fourth derivative of position vector, the t4, like that. So that is snap. So it means that here, if we talk about snap, we have, so if we talk about snap, right, it means it is such that we have, let me just erase all that. Okay. So if you talk about snap here now, that means s of t, you take it as s of t, that is equal to, now differentiate sine, now you get cos, then omega comes, you have 4 of that. So you have a omega raised to power 4 cos omega t in the direction of I. Differentiate cos, now you get minus sine. So minus and minus is plus. So you have a omega 4 sine omega t j. So it's periodic and it keeps going like that. So with this, we come to the end of this video on differentiation of vectors. So if you have not subscribed to the channel, be sure to do that, because you don't want to miss this very useful knowledge. Of course, be sure to subscribe, like I said already, and then hit the notification bell so you can always get alerted when a new video is released. And do not forget to comment, like, and share. Comment, for instance, that you want me to teach a particular topic I've not taught, or you want me to clarify something, and I might just find time to do all that. Until then, bye.